Mm-hmm. Newton's third law using the double subscript notation. Says FAB as a vector is equal to negative FBA. So something like that with I think it's possible I made a mistake, but I think probably what happened is if there's a circled sign there, it means that's mine and you didn't put a negative sign there. Okay, how about homework questions? Yes. Mm-hmm. Okay, yeah. Do you have it with you? I don't think I have. Okay. Oh, I have them here. 5. I have it here. Okay, so rigid body, free body diagrams. Number 5. So there's a pin that slides in a slot on a beam. And the other end of the beam is connected to the ground with a pin joint. And then in the middle of the beam, there's a pulley, and a cable goes over the pulley. I guess it looks like it goes straight up. Connects to the ceiling there, and to that end of the beam. And so if we're going to do a free body diagram of the beam, there are a few ways we can do this. The one that would be the most useful, I guess there are sort of two similar versions, is to include the pulley in your system of bodies that you're isolating. So it would look something like this. And now the forces, there'd be a weight here. There would be a cable tension there and there and there. A pin joint applies a force vector with an unknown direction, so we could call this like RB. So that's an unknown force vector. And then the pin in slot joint applies a force perpendicular to the slot. So you could do it up like that, or you could do it down. Either one of those is fine. If you guessed wrong in your calculation, the answer would come out negative, and that works just as well. So if you assume that it's this way, and you end up with RA equal to negative 1200, what that means is it's really going this way with a magnitude of 1200. It means the same thing. It means if you had originally assumed it was down, you'd get an answer of positive 1200. They tell you the same thing. Any questions about that one? Yes. Well, so that brings us to, so they're necessary if this is what you isolate, because just because of the rules of free body diagrams. But you could just as easily draw a free body like this, where you include that's pretty ugly, but no, that's super ugly. Okay, so include the cable, or even, you could think about it like this. So that part of the cable is part of the body you're isolating. Then you have the weight force, the force over here, the force RA. There's a cable tension here. But there's no cable tension here or here, because those aren't forces that the surroundings are applying to the boundary. Those are internal now to what we're isolating. So if you isolated it, if you thought about it this way, then you're right. I mean, your intuition was exactly right, but you should. So, but if this is what you choose to isolate, then those forces have to be there. Okay. Yeah. Yes. Yeah, sure. Yes, that's fine with me. Okay, there's another way you could do this, and that is just isolate the beam. A lot of this stuff stays the same. But now we have to think about what happens. So there's one more place where the outside world makes contact with the boundary, and that's where the thing that the pulley is mounted to connects to the beam. Okay, so now you have to think about what's the type of connection between the beam and the mount for the pulley. It looks in the picture like that's rigidly attached, that's a fixed joint. And so if that's a fixed joint, then you have to go, this is some kind of force. I'll call it the force on the beam by the pulley. And then a fixed joint also applies a couple, so I'll call that M. Which of these is preferable? If you were going to solve this problem, I mean, just add up the variables and you get a sense for which one you'd rather go with. Yes? No, we could, yes, you are right. There would be a tension over here, thank you. But there wouldn't be one here because the pulley isn't attached. Yes, thanks. Okay, so let's add up variables and see. So we have 1, 2, 3, 4 variables there. Here we have 1, 2, 3, 4 variables. Here we have 1, 2, 3, 4, 5, 6, 7 variables. So this is going to cause a lot of problems. Well, we could probably do it if we would do this, and then we would isolate the pulley and use Newton's third law, and all this stuff would go away. But if this shows the variable that you're trying to calculate, this is a quicker way to go. Any other questions about that? I suppose there's one more while I'm going through an exhaustive list. You could also just include that little mount for the pulley. And now, what's the connection between, so imagine that there's like a pin holding the wheel of the pulley to that mount. Well, then that's like a pin joint. It's a pin joint connecting the pulley to this. And so this would be like a force vector like that. But I think these are probably the two most reasonable interpretations of that. But I could have been a little bit more clear about specifically what I wanted. Okay, so then number 5 in the calculations. Okay. So this is rigid body statics. Number 5. There's a force vector of 400 newtons that way. There's a cable force this way, and I think we're given that this angle is 45 degrees. Well, for now, let me just draw that the way it's drawn in the picture. So that cable's connected to the wall. Then we have the center of mass of the body. And then over here, we have a pin joint connecting the body to the ground. The mass is 20 kilograms. And we want to calculate the external loads on this body. So the first step is a free body diagram. The 400 Newton force is applied to the left. The cable applies a force P. The pin joint applies an unknown force vector. So I'll call that RP for the reaction at the pin. And then at the center of mass, the weight's applied. That's 20 times 9.81, so 196.2. And all of the coordinates that are given use a coordinate system like this, with the origin at the center of mass. So we might as well put our about point here too, and then we can just use all those coordinates as the row vector. So row, force, MA. The row vector where the 400 Newton force is applied is negative 0.5, positive 0.02. Force vector is negative 400, 0. And the cross product is positive 8. Cable attaches to the body at 0.6, 0.4. So if the about point is the origin, this is 0.6, 0.4. The force vector is t times cosine and sine of 45. So 0.7071 t, 0.7071 t. And the cross product is 0.6 times 0.7071 t minus 0.4 times 0.7071 t. There might be a clever way to figure that out, but I can't think of what it would be. Oh, can I? Wait. Oh, I can. It's coming to me. No. 0.141. 1414. Is it something like that, or am I way off? Yes. 1412 t. And oh, that was so awesome. I'm going to tell my wife all about figuring that out later. She'll be so interested. And then the weight force is acting at the origin. So the row vector is 0. 0, negative 19.62. No moment. And the last one is RP. That RP, the pin, is at 0.05, negative 0.2. And the force vector is 0. No, thinking of the wrong thing. The force vector is RPX, RPY. And the cross product is 0.05 RPY plus 0.2 RPX. Okay, we have 4 loads on the free body diagram. We have 4 loads in here, so we're done. The Newton's second law. We just add up all these forces from the force column. So negative 400, 0, plus 0.7071 T, 0.7071 T, plus 0, negative 1962. That should be 196.2. Plus RPX, RPY is equal to zeros. And then the moment equation, just adding up the moments. So 8 plus 0.1412 T plus 0 plus 0.05 RPY plus 0.2 RPX is equal to 0. And that is 3 equations for 3 variables. The variables are T, RPX, and RPY. So you can solve that. Yay! That's when you have the same number of variables as equations, that's when you're happy. That's 8 plus, yeah. Any other homework questions? Okay. So now let's get into 3D problems. So 3D rigid body statics. And I'm going to start with an example because I want to point out how similar this is to 2D. Really, the only thing that makes 3D more difficult than 2D is that representing the joints gets more complicated. So once you get to the free body diagram, that's already been done, and the rest of the problem is pretty easy. So I'm going to start one with a free body diagram, and we'll just see how everything translates over. So let's say we have this rectangular solid. And the forces or the loads acting on it are a force straight forward, that's at the midpoint of that edge, with a magnitude F. We don't know what that is. Two components of a couple acting in the middle of the top face. So that component of the couple is 100. All these are in newtons and newton meters, so the couples are in newton meters. That one is 300 newton meters. Before I go on, let's think about what these mean. So, a couple of 100 newton meters in this direction. Which way would that, if this thing was free to rotate, which way would that make this body rotate? So remember, it has to do with the right-hand rule. So put your thumb in the direction of the moment of the couple, and the rotation would be like this. So it would like barrel roll this way. Okay, that's the 100. And then the 300, same approach. Your thumb goes that way, so that would spin it around like this. Okay. And I should point out, I think especially like early on, you do yourself a big favor if you try to visualize those couples when you see them. You know, you just kind of put this sort of rotational idea into your brain. It'll pay off not just in this class, but in all your mechanics classes coming up. So it's worth just taking an extra 5 seconds when you see those and just try to solidify it, you know. What else do we have? A weight force acting at the center. So that's at the center of the whole thing, of 588.6. So it's like this thing has a mass of 60 kilograms. And then over here at this corner, we have a force vector with 3 non-zero components. I'll call that the force vector B. And then over here, we have 2 components of a force vector, this way and this way. We don't have one going from left to right. And I'll call this one the force vector. Well, I'll just label these components. So I'll call this one AY and this one AZ. And so the coordinate system I'm using is X this way, Y this way, and Z this way. And we want to calculate F, B, and those components of A. How many total equations are we going to get from Newton's laws in a 3D problem? 6. Yep, 3 from the moment equation, 3 from Newton's second law. So the most variables that we can deal with a single rigid body is 6. So you might want to check that first. You know, if you have 7 or more, you're just out of luck. There's nothing you can do. It's not an algebra problem. It's just not possible. So here we have how many variables? 1, 2, 3, 4, 5, 6. So it should be good. It's not guaranteed because sometimes the equations can be redundant or whatever, but looks good. So for an about point, what do you want to choose as an about point? Yeah, there's 3 unknown force components there, so let's put it there. Okay, so rho, force, moment. And we're just going to have to go through all these. I'll start with the weight force. So what's a vector that goes from B to the center of mass of this whole thing where the weight's applied? Well, we can think of taking a path like from here along the negative x axis and then along the negative z axis and then along the positive y axis. So, oh, I didn't give any dimensions. Makes it hard, doesn't it? So this is 0.5 meters. This is also 0.5. And then the length is 1. Okay, so in the x direction, we go half a meter in the negative x direction. In the z direction, we go a quarter of a meter in the negative z direction. And then we go a quarter of a meter up. Anybody have any questions about finding that? The force is just in the negative y direction, so 0, negative 588.6. And if you take that cross product, I believe you get 147.15, 0, 294.3. Then the next force, let's do that force F. To get from B to where F is applied, we can go half a meter in the negative x direction, and then half a meter in the positive y direction, and we're there. So negative 0.5, positive 0.5, 0. And the force F is in the positive z direction, so that's just 0, 0, F. And the cross product is positive 0.5 F, positive 0.5 F, 0. And now we'll go to the force A. To get from B to A, we're just going 1 meter in the negative x direction. So the row vector is -1, 0, 0. Force vector has no x component, only y and z. So that force is 0, ay, az. And the cross product is 0, positive az, negative ay. And then the force at B, that's at the about point, so no row vector. All three components of the force, and the moment is 0. And now the only thing we haven't dealt with is the pair of couples, the x component and the y component of the couples. So we don't care about forces or row vector. We just have an x component of 100 and a y component of positive 300 and 0z. Okay, so Newton's second law, I'm going to move this over a little so I can... Okay, so Newton's second law says 0, negative 588.60 plus 0, 0, f plus 0, ay, az plus bx, by, bz is equal to 0, 0, 0. And the moment equation says negative 147.150, positive 294.3, plus 0.5f, 0.5f, 0, plus 0, az, negative ay, plus 100, 300, 0 is equal to 0, 0, 0. And we come up with 6 equations for 6 variables. And the variables are f, ay, az, bx, by, bz, 1, 2, 3, 4, 5, 6. Okay. Okay. So now we have reached the point in this class where we do not want to calculate this by substitution anymore. That would be a major pain. So here's how we're going to do it. Solving big systems of equations. Well, it works for small systems of equations too. It works for any system. Big systems of equations. And the technique is called reduced row echelon form. And this is the best way to do it because all of your calculators do this. And at some point, you'll or maybe some of you already have, but the rest of you at some point will take a class in numerical analysis or something where you'll learn mathematically how this works. For now, we don't care about that. It's just a way to enter it into your calculator and have this system solved for you. So the way we're going to do it is we're going to first set up a matrix. By big systems of equations, let's say, so let's call it n equations for n variables. Okay, so what we want to do is set up a n by n plus 1 matrix. This is the number of rows in your matrix, and this is the number of columns. Each row is going to represent one of your equations. Each of the first n columns represents one variable. And the last column represents the constant. Now you need to get your equations into this format. So put each equation into the format a times your first variable plus b times your second variable plus blah, 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 plus, c times your nth variable is equal to some constant, k. So the key thing with this format is all your variables are on the left. And your constant is on the right. If you forget to do that and you write it with all of your variables on the left and your constant over on this side, then your constant is going to have the wrong sign when you enter it into the matrix, and you're going to get the backwards answers. Well, if you did that on every equation, you would get the exact backwards answers. So you have to put it in that format or it messes it up. Now, for each equation, and remember, we're talking about the rows, so we're talking about going horizontally across the matrix. Enter the coefficient of each variable in the corresponding position. And then finally, once you have that matrix filled in, you just run on all TI calculators. It's called RREF for reduced row echelon form. Some of you have calculators with a linear equation solver on it, and if you'd rather use that, feel free. You know, this is just if you currently, you know, don't have a good way for solving systems of equations, this will work. So let's go through that with the problem that we just did. All right, so the first step, we're going to make this n by n plus 1 matrix. What's Rn in this problem? Yep, 6. So our matrix is going to have 6 rows, 7 columns. Okay, so 6 rows. And 7 columns. Each row I'm going to associate with one equation, so I'm going to number the equations. 1, 2, 3, 4, 5, 6. And then each column represents a variable, so it doesn't matter what order we put them in, but I guess I'll go F, and then A, Y, A, Z, and then B, X, B, Y, B, Z. And then the last column is the constant. And now I'm going to rewrite all my equations in this order. So the first equation just says Bx is equal to 0. I'm going to do this as solve this as a system of 6 equations and 6 variables, even though you'd say like, well, that's not an equation, that's an answer for one of these variables. Like you could, so yes, you could reduce down the number of variables you're solving for. That just tells us Bx is equal to 0. But I'm just going to enter this into the matrix as an equation, and it'll come out in the solution. The second equation from Newton's second law says AY plus BY is equal to 588.6. And please stop me if you have any questions as I go through this, or if I'm going too fast or anything. The third equation from Newton's second law says F plus AZ plus BZ equals 0. The fourth equation. So now we're done with the 3 Newton's second law equations. We can go to the 3 moment equations. It says 0.5 F is equal to positive 47.15. 0.5 F is equal to positive 47.15. And, you know, you could just solve for F and then reduce the number of variables, but I'm going to do it like this. The fifth equation says 0.5 F plus AZ is equal to negative 300. And then the last equation says negative AY is equal to negative 294.3. So this one actually, I think, wouldn't be too horrible to solve by substitution. So many things just gave you what they are, but we'll enter this in and solve it with the calculator. Okay, so equation 1. We have 1 times bx, so the coefficient of bx is 1, and the constant is 0. So 1 times bx, constant is 0, and everything else is 0. Equation 2, we have, so ay's, we have one of those. By's, we have one of those. And the constant is positive 588.86. And everything else is 0. Equation 3, F's, we have 1. AZ's, we have 1. BZ's, we have 1. And the constant is 0. Equation 4, F's, we have 0.5. The constant is 47.15. Everything else is 0. Equation 5, F's, we have 0.5. AZ, we have 1. The constant is negative 300. Everything else is 0. Let's see. And then equation 6, AY's, we have negative 1. The constant is negative 294.3. Everything else is 0. And now if you run reduced row echelon form, here's what you get out. So I'm going to write, it's going to give us back a matrix with the same size as what we put in. And it's going to be, so the first 6 by 6 matrix here has 1s on the diagonal like this, and 0s everywhere else, and that doesn't do you any good, but that's just what it's going to give you. The last column is what matters. The last column is going to give you the answers in the order that you listed those variables. So the first one, F, should say 94.3. If I did this all right last year. AY should be 294.3. AZ should be negative 347.15. And then BX should be 0. BY should be 294.3. And BZ should be 252.85. So there's F, AY, AZ, BX, BY, BZ. Yeah. But maybe the trickiest thing about 3D problems is coming up with the free body diagram in the first place. So to do that, we need to talk about 3D joints. When we talked about 2D joints, I started with a category of joints that introduced a single variable. Those were all just forces with one known direction. And then we went through all the other possibilities for reducing degrees of freedom. We talked about then joints that restricted all translation but allowed rotation. And then, since there's only 3 possible degrees of freedom in 2D, the only thing that was left was something that restricted all translation and all rotation. Okay, so only 3 possibilities. In 3D, just like we have 6 equations from Newton's laws, we have 6 possible degrees of freedom, 3 axes of translation, and 3 axes of rotation about 3 different axes. So we're going to go through a whole bunch of categories. I don't think there's ones in all 6, but there are just a lot of possibilities for how motion can be limited by joints. Okay, we're going to start with the same type that we started with in 2D. So I'll call this joint category 1. This isn't something that, like, people don't actually refer to these this way, but I'm just trying to sort of systematize thinking about it. And these are joints that introduce one variable into Newton's laws. The first one is a frictionless contact. So that would show up like, I'm going to just draw it the same way that I would in 2D. You know, if you have some object that's just in contact with a surface, I'll think about what that contact looks like. So if this is frictionless in its contact with the ground, the table prevents it from translating down into the table. So there's something going on there, right? That's one direction of force. But it still can translate along X, along Z, or however you have the thing oriented. And then it's totally free to rotate. It can rotate like this. It can rotate like this. It can rotate like this. And so the only thing it does is prevent translation into the surface.
How do you draw the surface? So not the object, but like
right.
surface.
How it can be sort of hard. Okay, so free body diagram. So there's the body. There's the surface, and the force is perpendicular to the surface, just like it was in 2D. The other joint in this category is a roller. And when I say a roller, I mean like a roller ball that can roll in any direction. So you can think of this as like a ball, not a wheel. Okay, so why do I want to exclude wheels from this? Yeah, wheels have a preferred direction, you know? They can roll one way, but unless you have a wheel that can swivel like a shopping cart wheel or whatever, um, if you try to move a wheel to the side, it has friction that restricts that motion. But so here we're talking about like the wheels on the bottom of a chair or something like a roller ball. Have you ever seen the movie Rollerball? It's pretty dumb. Okay, so there's the surface. And then I'm talking about like a ball. You know, something like that. This is a sphere. Um, yes, yes, more detailed even. I'm trying to make them look as understandable as I can. That's all. But if you draw them more simply than that, then if I do them with detail, then you can pull up my PDF if you can't figure out what your notes are. So free body diagram, there's the outline, there's the surface, and the force vector is perpendicular to the surface. Notice that for both of these, I didn't label this force, but let me call both of these N. You know, it's like a normal force. And notice that in both of these cases, N has to be positive because the ground isn't going to pull down on, this is a pushing contact. It's not going to hold it on. It doesn't prevent translation away from the surface. So N must be positive for both of these. Okay, now the second, so joint category 2. So these introduce two variables into Newton's laws. The first in this category is a wheel with a preferred direction. So that could be like this, where this wheel is going to roll in a direction like that. Okay. So let's choose a coordinate system for this with the x-axis along the direction that it can move. and the y-axis up from the surface, and the z-axis perpendicular to the line on the surface. Okay, so the z-axis is perpendicular to the line that it can move. So let's think about what directions this can move. Diagram. If this is the preferred direction, then there's a force vector that way that's perpendicular to the preferred direction. And there's also a force vector that way that's perpendicular to the preferred direction in the other plane. And these forces would be, this would be a friction force. I'll just call that F, and this would be the normal force. And now the other type in this category is a pin and slot joint. And this one I have a visual aid for, although it's broken. Damn it.